Hello, and welcome to this lesson on how we measure the rate of chemical reactions. In today's lesson, we will explore methods for measuring how much reactant is consumed or how much product is formed in a chemical reaction. We will then learn how to apply these techniques in different types of reactions, including those producing gases, solids, and precipitates. Previously, we discussed how the rate of reaction depends on the amount of reactant used or the product formed over time. But how do we measure these quantities? Today, we'll delve into the most common methods to accurately measure reaction rates in the lab. Let's get started. In some reactions, measuring the change in mass is the most effective method, particularly when a solid forms, mass increases, or a gas escapes, mass decreases. We'll look at both cases in detail. In reactions that produce a solid, precipitate, the mass of the system will increase as the solid forms. Here's how to measure it. Imagine a reaction between barium nitrate and sodium sulfate to produce barium sulfate, a solid precipitate, and sodium nitrate, a soluble salt. Firstly, set up the balance. Place a conical flask or beaker on the balance and record the initial mass of the reaction vessel, along with the solution, reactants. Next, add the reactants, for example, barium nitrate and sodium sulfate, and begin timing immediately. Start the timer the moment the solutions are combined to accurately track the reaction's progress. Every 10 or 15 seconds, record the new mass. This mass will increase as the solid precipitate forms within the solution. The mass increase corresponds to the amount of solid formed. Subtract the initial mass of the solution from each recorded mass reading to find the mass of the solid, precipitate over time. This method is useful because it allows you to monitor the formation of a product, like a precipitate, over time, and calculate the rate at which the product forms. In some reactions, particularly those that produce gases, the mass of the reaction mixture will decrease as gas escapes from the container. For example, consider the reaction between calcium carbonate and hydrochloric acid, which produces calcium chloride, water, and carbon dioxide. Let's go through measuring the reaction rate. Firstly, place the conical flask with the reactants, for example, calcium carbonate, on a balance. Record the initial mass before the reaction starts. Then, add the hydrochloric acid to the flask and immediately start timing as the reaction begins. Use cotton wool in the neck of the flask to prevent splashes while still allowing the gas to escape. As the gas escapes, the mass will decrease. Record the new mass every few seconds or at regular intervals, for example, every 10 to 15 seconds. To determine the mass change, subtract each measured mass from the initial mass. This gives the mass of the gas that has escaped. This technique is especially useful for reactions where the loss of gas correlates directly with the reaction progress, helping you calculate the rate at which reactants are being consumed. However, this method is only effective if the gas produced has a significant molar mass, like carbon dioxide. For light gases like hydrogen, the change in mass may be too small to detect accurately on standard lab balances. When a reaction produces a gas, another reliable way to measure the reaction rate is to capture the gas and measure its volume over time. This method is often more accurate than mass measurements for reactions producing light gases. For example, consider the reaction between magnesium and hydrochloric acid, which produces magnesium chloride and hydrogen. Firstly, attach a gas syringe to the conical flask where the reaction will take place. Then, add magnesium to the acid and immediately start the timer. As the gas is produced, it fills the syringe. Record the volume of gas every few seconds to determine the reaction rate. By plotting gas volume versus time, you can determine how quickly the reaction is progressing. An alternative method is water displacement. Firstly, submerge an inverted measuring cylinder filled with water into a water bath. The gas produced will displace the water in the cylinder. Then, measure the volume of gas collected over time by noting how much water is displaced from the cylinder. The method relies on using a gas that doesn't dissolve easily in water, as dissolved gas won't contribute to the measured volume. Some reactions result in the formation of a precipitate, which can cloud the reaction mixture. To measure the rate of this reaction, we can monitor how quickly the precipitate forms. For example, sodium thiosulfate and hydrochloric acid produces sulfur, which turned the solution cloudy. Firstly, set up a visual marker. Place a conical flask containing sodium thiosulfate on top of a piece of paper with a visible cross marked on it. Next, start the reaction. Add hydrochloric acid to the flask and start timing immediately. Monitor the visual change by observing the cross through the flask and record the time it takes for the cross to disappear. This happens as the precipitate clouds the solution. The quicker the cross disappears, the faster the reaction. This method has limitations. Firstly, it is more subjective because it relies on visual judgment. Different people may perceive the disappearance of the cross at slightly different times. Furthermore, only one data point is recorded, time for cross to disappear, making it harder to plot a full rate curve. Each method has strengths and weaknesses, and your choice depends on the type of reaction and products formed. To summarize, mass loss is best for reactions producing dense gases like CO2. It's easy to measure changes in mass using a balance. In comparison, gas collection is ideal for reactions producing gases like H2 or O2, allowing precise volume measurements. Finally, precipitation is suited for reactions forming solid precipitates, but less accurate and harder to quantify. In today's lesson, we explored several methods for measuring the rate of a chemical reaction. We looked at how changes in mass can be used to track reactions where solids are formed or gases are produced. We also examined how measuring gas volume with a syringe or through water displacement can give precise insights into reactions producing gaseous products. Finally, we discussed the use of precipitation methods to measure the rate at which a solid forms, though noting its subjective nature. By understanding these measurement techniques, we can effectively monitor and calculate reaction rates, providing essential data for both scientific analysis and industrial applications. We will look at how we can represent the data we obtained graphically in the next lesson. Watch the rest of the GCSE chemistry course at Sophos Education.